So let's check your homework. Your homework was to actually draw out the cell, labeling everything for this electrochemical cell, where zinc and copper are our two electrodes. We're not sure which one is the anode or the cathode. These aren't written in any specific form. We need to draw out our solution concentrations, anode, cathode, electrode flow, voltmeter, volt reading, and the salt bridge. So to figure out which one is being reduced and which one's being oxidized, so which one is our anode and which one is our cathode, we need to write out the reduction equations for both of these and go look at our table. So for zinc to be reduced, it must be going from the zinc ion to zinc solid, because that way would be a reduction in charge. So zinc 2 plus 2 electrons, becoming zinc. Then I do the same thing for the copper. In order for copper to be reduced, it would be copper. I know it's 2 plus because this 2 charge down here. So copper 2 plus 2 electrons makes copper. So I look these up in my reduction potential table. The zinc has a negative 0.76 reduction potential, and the copper has a 0.34 reduction potential. So looking at this one obviously has a greater potential to be reduced. So whichever one is reduced, red cat, this is going to be my cathode. And this one then must be my anode. So if I do my cathode minus my anode, so the E cell can equal cathode, so 0.34 minus my anode, negative 0.76, and I'm going to get 1.1 volts. So this is going to go in my voltmeter once I draw it all out. So I need to draw out my anode and my cathode, doesn't matter which order you do them in. So I'm going to put my cathode on this side. This is my cathode. I needed to label everything. My cathode is going to be the solid in the reaction. If there is not a solid, you got to use an inert one, so graphite or platinum. My anode, I'll put that on the other side. Once again, it's going to be my metal. So my metal is the zinc. This is my anode. I need to write the solution concentrations. Well, if it said I'm solving for E cell, I must be using 1 molar solutions. So for my cathode side, I have 1 molar CuNO3 2. For my anode side, I have 1 molar zinc NO3 2. I'll go ahead and draw out the liquid just because it looks strange without it. I'll draw in my wire, okay, to my voltmeter. On my voltmeter, it should be reading 1.1 volts. Now this cannot occur unless I go ahead and also draw in my salt bridge. Okay. And in my salt bridge, I'm going to use KNO3. Cell potential, electrical work, and free energy. So we're going to have a constant for these calculations. It's called the Faraday's constant. This is the charge of 1 mole of electrons is 96,500 coulombs. So we're going to be using Gibbs again. A lot of times I'll call this reaction the minus NF equation. Like always, if delta G is negative, it is spontaneous. If delta G is positive, it is non-spontaneous. In our equation, the N still stands for the same thing it's said for in the ideal gas law, and is always the number of moles. But because we're talking about electrons here, we're going to be talking about moles of electrons specifically. F is our constant, and E is the number we just learned to calculate using our cathode minus our anode. If E is negative, it means it's non-spontaneous, and if E is positive, it means it is spontaneous, which makes sense. Delta G and E are on opposite sides of the equation, so they have an inverse relationship. So if this one is negative, meaning spontaneous, this one must be positive, meaning spontaneous. Now, if you notice my unit on Faraday's constant, in this case I put joules over volts per mole. Even though I had coulombs there, that's because a coulomb is a joule per volt. So let's do a problem and actually use this equation. So using the table of standard reduction potentials, calculate delta G for the reaction. So I have the total reaction. I'm going to need to split this into its cathode and its anode reactions. So for my cathode, that's where my reduction occurs. I have copper 2 plus becoming copper 0. So notice the reduction in charge. That's how I know that one is my reduction equation. So I write what it starts as, copper 2 plus. It becomes copper. I balance my element that's there, 1 and 1. I balance my electrons, plus 2 electrons. That would make this neutral. So I have my cathode reaction. For my anode reaction, I have my Fe solid becoming Fe 2 plus. And the way it gained that 2 plus charge is it lost 2 electrons. Now if it did ask for me to balance out the equation, I would just combine these two, 2 electrons, and sure enough, this actually already was balancing the charges. To find my E, I do my cathode, the E cell. I do my cathode minus my anode. So I go look up on my reduction potential table, I go look for this exact equation, and I find it to be 0.34. So cathode minus the anode. So you don't have to worry about flipping signs or anything. You just use this equation and you don't ever have to worry about it. So the cathode minus the anode, I look up this equation and I find it to be 0.44, which gives me an E of 0.78 volts. Now that I have my E, I can calculate my delta G. So I have delta G equals a negative, because it's a minus, nunf, a negative. N is my moles of electrons. So what was the overall mole change of electrons? I start with 2, I end with 2. It has to be the same number on both sides. So it'll be minus 2 times Faraday's constant, 96,500, times my E, 0.78 volts. When I plug all this into my calculator, I get negative 150,540. Rounding for sig figs, I had 2 sig figs here and 2 sig figs here. So I round for sig figs and I get negative 150,000. Now for my unit, you could just go what you know. Well, you know that this should be joules per mole. Okay. Now the reason why I know it's joules and not kilojoules is because we started with volts. But I'm actually going to show you the units to make sure you understand why I knew that. So this was 2 moles of electrons per mole of the equation. Then 96,500, my unit here, was coulombs per moles of electrons. And then my unit for volts, now volts wouldn't cancel out, but a volt is also a joule per coulomb. So to look at what cancels, moles of electrons, coulombs, coulombs, so I get joules per mole. So this can be a little bit complicated, trying to actually write out the units because of the fact that coulombs could be joules per volt. And if you'd written it like that, then you could have left volts here. The volts would have canceled and joules would have been left. Or you can say it's coulombs per mole of electrons. So it can get a little bit complicated. I suggest you just remember that delta G is either going to be kilojoules or joules per mole. In this case, delta G is always going to be joules per mole for calculating for electricity using the delta G minus Nunf equation. So anytime we're talking about electrochemistry or these redox reactions, we're going to be talking about joules unless somehow you actually went and converted to kilojoules, because all of our volts and all of our coulombs are just in joules, not kilojoules. So for our next problem, it says using the standard reduction potentials table, predict whether 1 molar HNO3 will dissolve gold metal to form a 1 molar Au3+ solution. So what this is asking is will this be a spontaneous reaction? So for the actual reaction, we're having HNO3. We're reacting with gold. So when we look at the products, this is going to be a single replacement reaction. The H goes out, the Au comes in. Okay, remember that's one of our main types of redox reactions. So I have an Au NO3, which Au is a 3 charge, so I put the 3 here. Plus, if the H got kicked out, it's released as H2 gas. So to give you a little hint, the reason why you're always given equations like this, notice they're ions and not in the compounds, is because we actually use net ionics to make it a heck of a lot easier. So let's do that. Let's get rid of our soluble ions. So that would leave this as 3+. So now if I actually look at this as H plus Au makes Au3 plus H2. I can write out my two half reactions. So my H plus is going from positive to 0, so it's reducing from plus to 0. So for my cathode side, I have H plus becomes H2. I balance out the elements I have there first before I do electrons. So notice I have 2 hydrogens here. I have to balance that out with a 2. Now I look at electrons. Each hydrogen loses 1 electron. There are 2 hydrogens, so I have 2 electrons to balance out this problem. On the other side, for my anode, I have Au gold becoming Au3+, balance out the atoms that are there, 1 Au, 1 Au, then balance out the electrons plus 3 electrons. I check and it does not actually ask me to balance out the equation, so I won't worry about the fact I have 2 and 3 electrons. All I need to do is look for their E overall. So my overall E is my cathode minus my anode. So we have your E equals, I look it up on my table. Well, remember hydrogen is the basis for all of our reduction potentials, so that is our 0, that's our starting, so 0 minus 1.5, which gives me a negative 1.5 volts, and this is non-spontaneous. So what happens if we have a voltaic cell in non-standard conditions? So remember our standard conditions are having 1 molar, 25 degrees Celsius, and 1 atm. Well, now we're going to use Le Chatelier's principle. Okay, so a little bit of equilibrium's coming back in here. So all we're going to be doing is looking at shifts. If we look at this overall problem, it asked for our E cell. So we need to find our original E cell to see what changes. Predict whether the E cell is larger or smaller than the E cell for the following equations. Notice the difference between these two is only the not symbol. You need to know what that means. So predict whether the cell that's not at standard conditions will be a larger or smaller electron potential than the cell at standard conditions. So for our cell at standard conditions, I look up my two half reactions. So I look up the one for my cathode, which is the one that got reduced. So my cathode was, well, manganese went from +2 to 0, so that must be it. Mn 2 plus 2 electrons makes Mn. I look that one up on my cell potential table, and I find that to be a negative 1.18. I look for my anode, thing that was oxidized, aluminum. Went from a solid to the ion, aluminum 3 plus, by losing, that's a 3 plus, by losing 3 electrons. I looked that one up on my potential table, and that one is a negative 1.66. So cathode minus anode, and that gives me, I'll write my answer over here, 0.48 volts. So written as it is, this was spontaneous. To predict what would happen if I change my concentrations, we're just going to look at add away and take towards. So if I make my aluminum concentration, my aluminum ion concentration greater, we're going to do add away, which means we're going to shift towards the reactant side. And if I shift towards the reactant side, then this reaction is going to occur less often, so we're going to have less energy. So overall, my E cell, so this specific E cell, should have less transfer of volts, less energy change, the reaction's occurring less. So it's going to be less than the standard condition for the cell. Whereas if I leave the ion concentration the same, but increase the manganese ion, then in this case, if I increase that one add away, then we're going to push towards products. So if I'm forcing this reaction faster towards the products, we're going to transfer those electrons more rapidly, so the E cell will be greater than what the cell would have been at standard conditions. So basic Le Chatelier's principle stuff. So using these concentrations, we can construct a cell where both compartments can actually contain the same components. So if I have silver metal, and I have different concentrations of the silver nitrate, I can still force this reaction to occur based off of this concentration difference. Because I've created such a positive atmosphere on this side, notice 1 molar of Ag+, whereas only 0.1 molar Ag+ here. Because I have such a positive full over here, I've created a driving force to transfer electrons from the left to the right. And the same thing will happen where my silver starts degrading on this side and starts building up on this side. So for number 5 then, I look, once again, I have a higher positive pole over here, so I know that my electrons will be flowing in this direction. So to designate the anode and the cathode, just look at fat cat. From the anode to the cathode. So if my electrons are starting here, then this must be my anode, and this must be my cathode. So a quick review of what we talked about. A negative E is always non-spontaneous, positive is spontaneous. This would be a good battery. It just occurs. It keeps the electricity running. When E equals 0, we're at equilibrium, and we have a dead battery. Just like when delta G equals 0, we're at equilibrium. Equilibrium means exactly equal forward and backward. Electrons are going forwards and backwards, and nothing is occurring for your poor little electrical device that needs that battery. For our delta G, it's negative, means spontaneous. Delta G is minus nunf. We use all of our little variables in here. So our favored conditions is when our E cell is greater than 0 and our delta G is less than 0. So to practice bringing this all together, this exercise 6 is going to be your homework. You're going to be drawing out the cell, labeling absolutely everything in here. You're going to be writing out the molarities, write out their half reactions, find the overall E of the reaction, and solve for your delta G. Finally, at the very end, I'm going to have you apply that whole equilibrium shift constant idea. So for you to be able to check your answer, I'm going to give you your final answer for delta G. Still got to show me all your work. But your final answer for delta G should come out to be negative 20844 joules per mole.